Because I'm saying.
That.
At Bryce, and I think I'll have like 1 teacher there. So this time I thought I can't better just pop in and buy some items once. Yeah. Instead of the buffalo, it's like how you record it. It's yes. The American flag. Yep. How many people have made all these different things? Like someone designs that shirt, someone buys, and then so yeah. There, and you can see how it's someone designed it.
If you want. I was also just looking at the fact that it looks like the. Probably, yeah.
Like if you're standing here,
Yep.
forward just a step. How is it?
Yeah. The only issue is, can you see the screen?
Oh,
that's awesome.
At least you can,
That's like pretty subtle.
Maybe. Yep. Maybe like right here. Actually, yeah, that's pretty good. Yeah, you're perfectly framed in there. Okay. Yeah, yeah. What if you come forward a little bit? Okay. Yep. Turn it more like right about there-ish. Perfect.
Now you gotta watch.
Of course.
They don't wish you were dead.
That's a cat version of love. I don't actually wish you that. Maybe kind of cat socks.
Looking suit.
Thanks.
It's not Skippy that can't watch it. It has some other people that wanted to see it, wanted to know if they could.
Oh, yeah, yeah.
Greg's all set up and ready.
We can write it off.
Can you ask him if you can see everything? See and hear stuff? Sarah, do you know where there's a water fountain close by?
I can go find them.
That's a mustache to remember.
What's up, Tyler? Yeah. Hey. How's it going? Did I just see on Facebook that you got to act in just like a crazy trip overseas?
Yeah, I was I'm still pretty jet lagged from it.
All right.
Yeah. Gotta write 2 HG presentations this week, so.
Oh, you're doing 2?
Yeah, I got invited for one just because I was talking about last year. Fortunately, now it's like generic overview, so I could basically just
Like use stuff that you, yeah. Yep.
Oh, yeah. It's gonna be like, it's actually a really great format. We start with like a 2-minute talk in which you're supposed to just like very, very quickly summarize your research to a general audience, and then after that, there's kind of like a posting session. Yeah. So we're doing posters based off of like a 2 months or so. We're like scroll the columns of data. So this has like a very good overview and also like so, right. Should be interesting, but yeah.
Oh, she can see it.
Okay.
See it.
They can see it?
Yeah,
And can they hear? Okay, like if I
Not for any of that. So, yeah.
You look very ready.
what?
Ready.
Thank you.
So you do great.
I feel ready.
That's good.
The exposure seems to jump around.
Here.
Oh, does it?
Yeah. Is there a way to manage the exposure?
I'm not sure.
Probably got some sort of auto feature.
Probably. Yeah, I'll take it. Thank you.
It's doing it for Scott.
Yeah.
Those are my kind of like the top.
Yeah, that's what I'm
Jen
planning.
said she can hear.
Okay.
I was watching you too.
Cameraman. Broadcast the largest.
We need to approve meeting members.
Yeah, committee members will probably be right here. There's only 3 of them that are going to be here physically.
Okay, so there's.
Yeah. So those seats are all open. Yeah.
Oh, yes.
He was having fun.
Daniel, are you there?
Yes.
Fantastic. All right, you're coming through. Can you see the screen all right? Hear me all right? As in you don't see a you just see the screen and not me. Okay. I think I can set it up so that you can see me as well. You can do yours. Okay. So Peter's going to sign on, and he's going to use his laptop to set it up so that you can see me. Oh, Scott, you're here too. Awesome. Fantastic.
Going back to the two thoughts,
Fantastic. All right. So everything's coming through. Sweet.
So we're just missing your committee.
Yeah, we're missing my committee. And it's now, hi. And of course now it's time to start. And before people show up, we've got plenty of extra chairs.
Don't worry.
Oh, Hunter's here too. Hi, Hunter. These seats are actually taken.
I figured.
Yeah.
Scott, are you so much?
I don't know if there'll be more people showing up or not, so putting out a couple probably wouldn't be a bad idea.
Oh, that's my fault.
Yeah.
So this one's straight to YouTube. So these guys, that's not interfering with these two. Good morning, Dad. Yeah, so Daniel and Scott, we are just currently waiting on Davin and John Evans.
There you go. Should we do one more computer?
Yeah, I mean, honestly, I feel like we should. I can put my computer right here.
Yes. So, especially any of my students, did any of you bring your power cord for the new Macs?
How's your battery on that one doing?
It's like 83% now.
Okay.
Soon.
Okay.
I'll turn down the brightness.
Lindsay's is like 90 something.
Lindsay's is almost to 100, but I'm not sure. They would both probably drain at the same rate.
Wow. This is really smaller. Might be a little bit slower.
But that has a larger battery.
We can switch over halfway.
Yeah. If I see something come up for battery life, I can easily just hop in.
Is there one in the office?
Which office?
Yours.
Yeah, but it's too far.
I wouldn't worry about it. It's way out of the way. Yeah, Daniel and Scott, you can see me now, yeah?
Yes.
Fantastic.
You look sharp.
Thank you.
Happy haircut.
Oh, wait.
Oh, wait, there's one.
I did bring my keyboard.
Uh-huh. Tommy, there's a bunch of seats over on this side.
Okay.
Oh, I did.
And now I'll know where my boundaries are. They'll have cables boxing me in, right?
You can go do this around shipping. That'll be in the
That'll be the definition of success.
Yeah.
Scott, now you know what I mean.
Oh yeah, you had a cable that like ran like
I
right.
had to wait 45 minutes, half an hour just to drop.
Oh yeah, that's great.
Maybe on like videos.
Hey, his head didn't feel bad. Yeah.
Morning, Davin. Get right nice up front.
show in stereo here.
I should put one with the blue tint, one with the red tint,
Yeah.
and you can see it in 3D, right? That's how it works.
It's got a lot of nice graphics.
I'm neither. I can send him a email. Oh yeah,
Ask him where he is.
yeah.
As long as we know he's on his way, we can just get started.
Great. Then.
Oh, there he is.
Oh. Hey, John.
It's like walking to Onosuke yesterday.
You know what they say about the sunshine.
Yep.
All right. Cool. So with that, we're going to get started. Welcome to the PhD defense of Scott Wieland. Before we begin, I wanted to introduce his committee. So we have in person here Professor John Evans from Aerospace, Professor David Hinza from Mechanical, and then logging in remotely are Daniel Levescu from Los Alamos, and then Scott Reckinger, who is, where are you currently, Scott?
St. Mary's College.
St. Mary's College. You know, Scott's work actually led into the work that Scott Wieland did. There's lots of Scotts here
Too many Scots.
today. And so you know, I think we should also acknowledge the fact that this project, and actually Scott's PhD career, began with Oleg Vasilyev. And over the last year and a half, we've been fortunate enough to have Scott in my group. And you know, he's actually been fits in well the similar research, and I've actually been very lucky not just to work with Scott, but also to work with him on this research, learn a little bit about what he's doing. I think you can tell by the number of people here that Scott has had a pretty big impact on the community, and not just CU and mechanical engineering, Boulder more broadly. He is certainly a fan of beer, and really specifically I feel like that has to be acknowledged up front. He did look for a postdoc at a brewer, maybe still in his future.
Maybe. TUM Munich, TUM, they still might have another opening at some point.
All right, so
I mean, simulations of process control for brewing. What more could I want?
it's a fluids problem
Yeah.
of sort. And actually, in my reactive fluids course, Scott did a project on the reactions, biological reactions that occur during the brewing process. So he always tries to find a way to incorporate it. Although I don't know if there's anything related to beer here.
Maybe there's a surprise.
Okay. Nothing I've seen. So with that, I'd like to hand it over to Scott. And the way this will work is for the first 45, 50 minutes, Scott will present, and there will just be clarifying questions, either from the audience or the committee. After that, we'll have the more in-depth questions from the audience, and then all of the audience, and especially the parents, will leave the room so that we can grill Scott.
This is the fun part.
Yeah. Sometimes parents want to defend.
Maybe I'll accidentally leave the YouTube stream on so we can come back.
So, and then we'll have a closed door session just with the committee. Scott. So with that, Scott, you can take it away.
Awesome. Thank you very much, Peter. Welcome, everyone. Thanks for coming. I feel I'm truly part of the lab now, part of the Tesla lab, because it's customary that in all of our slides we have this wonderful image of flames. And so now that I've added that into my slides, I really feel like I belong. That's what I was missing. Of course, I need to start off by thanking my committee members for being here and working with me and helping me out. I have to thank my lab as a whole, and also Los Alamos for the funding for being able to do this. And then thank you all for showing up. So I think my parents would agree there's been a lot through my life that just has never changed. I've always been pretty constant. My head has always been in the clouds, and I've always had to have a deep understanding of how things work, really break things down to their base level. The convenient part about this is, as in the physics community, there's a lot of people that have this same problem. Their heads are in the clouds. And actually, these two, Lord Rayleigh and Sir Taylor, were the ones that started my project. And it started by them looking at clouds. They saw these odd formations in the clouds, and they wanted to figure out the physics describing how they developed. And because of this, they were able to develop the theories that have become the basis behind what's called the Rayleigh-Taylor instability. And so today, that's what I'll be talking about. To give you a little bit of a roadmap of what we'll be going through today, just went through the brief introduction, but then we're going to go through an overview of some of the Rayleigh-Taylor instabilities some of the Rayleigh-Taylor instability stuff that exists now, and this really mostly the things that are relevant to the work I'll be presenting. Then I'll touch base a little bit on the numerical method that I'll be using to run the simulations that I'll show later. Then of course we'll get into the actual simulations, the bulk of the work that I've done. The single mode result will probably be the longest section, and we'll see when we get there that I've got another little roadmap for us within that section. Then we'll get into the multi-mode results, and we'll finish off with some conclusions and work. So what exactly is a Rayleigh-Taylor instability? Well, it's a system of two fluids where we have differing densities. We have the fluid in red here, row 2, is a heavier density than the row 1. Now in the classical incompressible case, the two densities would be constant. You'd have one heavier constant density up top and one lower density down below. And then the key to this is that for the instability to occur, you have to have this density jump in one direction, but your gravitational force acting in a different direction. So you need an accelerative force in the same region that this fluid exists. Most of the time it's gravity, but you can also have accelerating fronts or various shock waves that could cause this instability. Now, to really explain what's going on, I figured today I would do something a little bit more unique. Being a computationalist, I figured it'd be kind of fun to just show everyone firsthand what a classical Rayleigh-Taylor looks like. And so what we have in this container is a system of two fluids where the blue fluid down below is the heavier fluid and the clear fluid up above is the lighter one. So right now you can see it's in a completely stable stratification. I can shift it back and forth, and we just have a little bit of a gravity wave that travels throughout. And you can see that it travels at a relatively slow pace. But the real key is when I take this, this vessel and I invert it, we'll have the blue fluid want to drop down below the light fluid. And so what I suggest you do, it'll happen pretty quickly when I flip it, focus on one section and look for both the motion of the blue fluid going downwards and also the clear fluid going up. And so with that, you can see how complicated this simple instability can get. There's a lot of different effects between the modality, and here we have surface tension and wall-bounded effects and all sorts of things like that going on. But to really get more specific, we can talk about getting into more detail. So we normally classify these systems by the Atwood number, which is a measure of the density difference between the two fluids. In this case, our Atwood number was about 0.01, which is in the lower regime. It's in the low Atwood number, which is what I'll be focusing on today. But our Atwood number is bounded between 0 and 1, with 1 being an infinite difference in density, and 0 being the exact same fluids. So based on that, they do have some predictions on the Atwood number, and you can kind of pick it up into different. Below an Atwood of 0.2 is considered low. Between 0.2 and 0.5 is kind of moderate, and above 0.5 is really high. But really, we're focusing on the low Atwood number because that's the one that exists most naturally in nature. So to get more in detail about what happened what happens in this growth of the instability, we start with the initial conditions. We have the heavier fluid on top of the lighter fluid, and in the case slightly different than what I showed in the apparatus, if we have miscible fluids, which is what we'll be talking about today, we then go through a diffusive growth regime where the two fluids just begin to diffuse into each other. From there, the perturbation that we apply to the interface will begin growing, and we'll be able to figure out how this will go from linear perturbation theory. And we call this the exponential growth, because it's the exponential growth phase, because it's the growth of the instability can be described by an exponential function. From there, we get into the regime in which we can describe it by the potential flow theory, and hence we call that the potential flow growth regime. From there, as long as our Reynolds number is high enough so that we have a low enough viscous effect, we'll enter into a reacceleration regime in which the fluid begins reaccelerating, and then we'll actually finish in a chaotic development regime in which it becomes turbulent-like and very hard to predict the velocity at any given point. Now, if there's other effects that stunt the growth of the instability, it's predicted that we'll end up in a self-similar regime. We'll end with a constant velocity, more or less, where the bubble and spike continue growing at about the same rate. And it would be regardless of initial conditions. We would lose all thought of the initial conditions from there. So where exactly do we see Rayleigh-Taylor instabilities? Really, it's all over the place. Here, I took a couple of pictures from Gene Hertzberg's FlowVis class. It's actually a favorite instability to photograph for that class, just because of the ease of the experimental setup. On the left image, they've simply just dropped India ink into water. And so the India ink is heavier, so we develop it Rayleigh-Taylor as it drops below. On the right, what I think is a little bit more exciting is this image that I know Scott Reckinger used in his thesis as well, in which they're pouring cream into tea. So pretty much every morning as we put cream into our coffee or tea, we experience Rayleigh-Taylor instability as the two mix. But there's also a lot of other places we can see this. One of my favorite is in cloud formations. On the lower left here, you can see the image that I showed before that kind of shows a very, very distinct Rayleigh-Taylor view. But if you look up above, some rare cloud formations like the Mammatus clouds, where you get these really cool bubble forms, that's actually caused by Rayleigh-Taylor instability. And then same with hot volcano plumes. That's really air that is lighter being heated by the volcano that is rising up and forming into an instability. But in our case, we're an engineering department, so we want to focus on more engineering applications and physics-based applications. And so there's a bunch of different scenarios that will come up, but here I've chosen 3 that are of particular interest to us. One, and probably the most, especially to Los Alamos, is the inertial confinement fusion, in which the Rayleigh-Taylor instability actually causes a mixing of deuterium and tritium that will actually take away the potential energy and take away the amount of energy that we're able to get from a fusion reactor. So the idea is if we were able to limit the mixing from the RTI, then we might be able to get better, more efficient fusion reactions. In the terms of U-shaped jet burners, they're kind of these unique and interesting burners that are being researched right now, in which in the actual burning reaction, they use RTI to mix the fuel and oxidizer to cause the reaction to happen. But then in supernova, you can see here that you develop all these fingering structures that come out, and those are actually Rayleigh-Taylor instabilities that are being caused by the accelerating front of the supernova that is exploding. Now, one thing that we have in common with all of these is that they all are highly compressible systems. And before, in the classical case, everything was incompressible. So there's a lot that we just don't know because the incompressible case has really been the case that has been studied. And the compressible case is still in kind of its fledgling state for being understood. So to give you an idea of some of the background that's been done, you can essentially break it up into 3 different scenarios, into theory, experiments, and computations or simulations. And so I figured we'd start with the theoretical predictions. And here I'm just going to go through a little progression of the description of the exponential growth phase. And so here our eta I expresses the location of the interface that is dependent upon our horizontal directions, our x2 and x3, where x1 is our vertical up and down direction. And then eta A is the amplitude of our perturbation that we apply to the interface. And then K2 and K3 are just our wave numbers of those perturbations. And then here T is time and N is our growth factor. So essentially that's N is the goal to be able to predict in this phase. And by predicting N, we'd be able to determine how things grow. So in the simplest case, we're looking at incompressible, inviscid, and immiscible fluids. We have a nice simple expression to predict this N. That's just based on A, which is our Atwood number, G, our gravity, and K, our wave number. But then it quickly becomes much more complicated as we start including additional physics. So if we add in viscosity and diffusion, then we get this function in which psi is a nonlinear function that we can't solve analytically, and we actually have to solve through numerical methods. And then V here is our viscosity, and D would be our coefficient of diffusion. But then if we take this one step further and we switch from the incompressible to the compressible regime, we end up with this lovely equation that also has a pretty large effect that's based on gamma, or the ratio of the coefficients, our specific heats. And so you can see here that quickly, this equation gets much more complicated as we add in more and more physical effects. And it's also important to notice that this is only for describing the very early stages. As soon as we pass through the very, very beginning and we start developing real vorticity in our fields, this is not even valid any further, and we have to go to potential flow theory. It gets even more complicated than there, and then past potential flow theory, we don't have a good way to predict how compressibility will factor in. So in terms of experiments, there's been a bunch of different experiments over the years. Here I've kind of categorized them in 3 different scenarios. One called the rocket rig, where you essentially fill it with the fluids in a stable stratification, and then use rocket engines to change the acceleration by accelerating it so much in the opposite direction. The overturning tank, which is pretty much exactly what I showed you guys before, where you just flip a tank upside down and see what happens. And the sliding barrier, where you pull a barrier out between the 2 fluids. The problem with these is, in order to factor in compressibility, you have to deal with gases to really get the compressibility effects that we're going to be looking at. And it's very hard to control the exact stratification that results from putting in the gases and trying to control the compressibility effects. But then on top of that, it's also very hard to predict exactly what perturbations you'll get, or be able to exactly match your Atwood number. And so you can get very much useful information out of the experiments, but there's still things that are left to be really investigated from the pure physical sense. Then we can go into simulations. And you'll notice here that I also include one experiment just to give you guys a picture of what a stratified, so as opposed to having completely compressible fluids, they just use stratified fluids in which they were able to control essentially the salinity of the 2 fluids. just so you could have a comparison to these other simulations. But then we've got the alpha group collaboration up here, in which they actually tried to, they simulated incompressible fluids with a compressible code in order to try, just because it was simpler for them. And in this case, they just worked in a very low Mach number limit. So they tried to work in the very nearly incompressible limit. Lafay et al., they kind of were in the forefront of looking at compressible simulations. And they looked at things that are very similar to I'll show later. And then Gauthier, he went through and essentially extended Lafay's work to the multi-mode and full 3D regime. Now, these cases are all well and good and have actually uncovered a lot of useful information, but the entire span of compressibility effects has not been explored, and there's still many more parameters to play with and tune and see how they affect what happens. So if we come back to these three engineering scenarios, I mentioned that we want to play with a bunch of different parameters in order to tune what happens. Well, essentially, in each of these scenarios, we can figure out an effect that we want to gain. And the question is, how can we gain them through harnessing natural effects that we can get from the compressible RTI? So for these U-shaped jet burners, we want to be able to maximize the growth of the instability, because we really want as much mixing of the fuel and oxidizers so we can have increased reactions. For the ICF, we want to minimize growth. As I mentioned before, it's the growth of the instability that saps away the potential energy that we want to be able to harness. And then for supernova, we really just want to understand what's going on. We really have no idea what's happening in supernova, so we just want to get a little bit closer to being able to maybe judge the age or predict how much further it will grow or something along those lines. But we can really also take this one step further, and we can ask the questions that we really want to answer. Most importantly, simply put, what effect does compressibility have on RTI? But we can go much further than this. As I mentioned, there's a lot of parameters that we need to investigate. So how does viscosity interact with this compressibility? How does the modality of the perturbation factor into this? How do all the various thermodynamic variables in the state that we're in, how does that factor in? But then finally, going back to that previous slide, how can we harness these benefits in order to make a useful prediction? So to do this, to really investigate this, what we're going to do is we're going to use high fidelity direct numerical simulations. So we're going to solve our equations exactly. We're going to do this for compressible and miscible RTI. To do this, we're going to need domains that are much longer than they are wide. So you can think about it in the sense of this apparatus, where I have one really long RTI. In this case of our simulations, we're actually going to flip this so that our RTI is going to be tall along these lines. For that, we will have a, we're going to make it about 16 times longer than it is wide. If we're solving this exactly and using the resolution that we need at every point in space, for a single 2D simulation, we'll require about 250 million points just for one 2D simulation. So if we factor in a third dimension, then this is going to increase by another 4 orders of magnitude, essentially. And then, so we really can't do that. We really can't afford that. So how are we going to solve it? We're going to use fancy numerical methods to make an adaptive grid. So on that, we'll continue on to a brief discussion about the methodology that I've used today, the parallel adaptive wavelet collocation method. So for that, essentially, like I mentioned before, we're going to do direct numerical simulations. For this, it means we're going to be numerically solving the compressible continuity energy Navier-Stokes equation, plus we're going to wrap this together with the mass fraction transport equation so that we could track the species of the fluid. And then finally, we're going to have to wrap it all together with the ideal gas law, so we have an equation of state. The top and bottom of the domain, we're going to put diffusion buffer zones in to absorb any shock waves from the initial conditions so that we can diffuse those out and they don't interact with instability. But then the rest of the boundaries we're going to take periodic. Periodic boundaries are just really convenient, and they are pretty easy to implement. So for these simulations, our finest level of resolution will be 1/4096. So we're going to have just over 4,000 points for every 1 unit of space. And then in terms of the convergence and the validity of these simulations, those I really talked about in my comprehensive exam, as well as they were talked about in Scott Reckinger's paper from 2016 in JCP. So if you want to get more into that, we could talk about it later, but I just don't have time to really get into the specifics today. So essentially, the idea is simply that we take a function here, shown here on the left, and we convert that into, we transform that into wavelet space, which gives us a series, a summation series based on coefficients and the wavelet basis functions. Then from there, what we can do is we can apply this thresholding filter, epsilon, in which we only retain the points in which our coefficient d here is larger than our epsilon. So essentially, our d will vary, will become greater in areas where we have greater variation. So if we look at our function here on the left, we obviously have the greatest variation right here on the center line. So when we look at the coefficients in wavelet space, we end up with, right here on the center line, we have significant coefficients all the way out to the finest level of resolution. So that essentially means we keep the finest level of resolution centered right on this area of variability. But then once we get away from the center line where we have a very flat, unchanging function, our coefficients become small. And when we apply the thresholding filter, we can get rid of all of them. We don't need them. And we can still get a very accurate representation of this function. Now, what exactly does this gain us? Well, it gains us very highly adaptive grids. So if we look here at a simulation of an instability, and we'll get more into the parameters of this exact simulation later, and we zoom in on one section, we can see that in this first image, you can see that you can kind of pick up the grids away from the interface, away from the actual instability growth itself. Where nothing's happening, we can have a very coarse resolution. But as we zoom in and get closer to the interface of the red and blue fluids here, you can see that we get a finer and finer resolution as we approach the actual interface between the two fluids. And that's because that's essentially where all of the interesting physics is happening. It's our area of greatest variability. So we're able to retain the points right on the interface where we need to resolve everything. But as we get away from the interface, we're able to have a very coarse resolution. And essentially what this gives us is, I mentioned that 250 million points before, we can take that down to about 8 million points. So we're gonna decrease that by about 2 orders of magnitude, which gives us a huge saving. It works out to be roughly 3% of the predicted number of points if we used a full resolution. So based on this though, we have to choose, we have to pass a function through this adaptation parameter. And the question is, how do we want to determine the adaptation? So we can come through and we can test a couple of different parameters from our flow evolution and see how they affect the grid. So if we look at just the species mass fraction, we end up with some decent capturing of the interface. But you'll see here that our finest level of resolution really gets to the 4th level. But if we instead adapt on the gradient of the species, the gradient of y, we can then get even finer resolution wherein we get all the way down to level 6. So that means essentially here we'd be a factor of 4 in each direction coarser, and here we'd be 4 finer. But then we can look at other parameters too. We can say, check out the velocity. Obviously, we don't capture all that much by looking at just the velocity field. But if instead we convert our velocity field into the vorticity field, we actually capture everything very, very well. But even more than that, we can take it through and look at something that even further developed, that has a huge impact on the instability growth, namely the baroclinic production term. And you can see that that really gets us a grid that refines around the entire instability. And so now you may be asking, so what do we adapt on given this? Well, the answer is, in practical purposes, we choose to adapt on all of these so that we can superimpose all of these grids together. And that allows us to get the perfect grid that captures everything that we need. So based on that, we can now proceed into our actual results. So for our single mode results, first I'll talk us through the initial conditions that we need. So I mentioned the Atwood number before. The Atwood number I showed before was for the classical incompressible case where we have a constant density above and below the interface. But when we get to the compressible case, we have to convert that into some sort of function that allows us to determine it based on not just the density, but something that would remain constant even though the density is changing. So we base it on the molecular weight of the fluids. But in the end, this really comes down to and equates to the density jump at the interface still. So if you looked at the density on either side of the interface and replaced W1 and W2 with rho 1 at the interface and rho 2 at the interface, it would work out just as well. We'll take our Schmidt number and we'll keep that at unity so that our diffusive effects and our viscous effects stay on the same level of interaction. We'll look at our Reynolds number, and here it's important to note that we're starting with a hydrostatic, we're starting with no motion in the fluid, so we don't really have a velocity to judge our Reynolds number on. So we use what we call the Reynolds perturbation number, which looks at essentially the potential of the instability, where we look at the gravity wave, and then the viscosity, and then the effects of the Atwood number. And we'll be looking at a range from 5,000 to 20,000 for this. And then we'll look at what we call our Mach number. This Mach number is not the typical Mach number that we're used to seeing. This is what we call the isothermal Mach number. And again, this kind of relates back to the Reynolds perturbation number in the sense that we don't have a velocity to really compare to initially. So we base this kind of on the potential Mach number, more or less. And so we look at the speed of a gravity wave in comparison to the isothermal speed of sound. And we'll look at a range of Mach numbers for this, and you'll see in a moment that this, in addition to accounting for compressibility effects, this also affects the stratification, the changing of the density in the fluid. So, yeah.
Can you comment on the significance of this Atwood number?
On the significance of this Atwood number?
Why you use 0.04?
So we use 0.04 because that's in the low Atwood number regime. Like I mentioned, the low Atwood number is the one that we find most commonly in nature, but it's also for convenience sake so that we can compare directly to the incompressible simulations that Daniel published a few years ago, where they looked at the Atwood number 0.04. And so it gives us a one-to-one comparison. Mm-hmm. So in terms of our initial state for setting the stratification I mentioned, the two equations we have to obey for this are we have to obey our hydrostatic equation, we have to obey our ideal gas law. But you'll notice in this that we have two equations, but we have three unknowns. We know our gas constant, but we have P, rho, and T, all that we don't have an equation to set. So what do we do about the third parameter? We have to choose something for the third parameter to be. So our initial thought was for our simulations, what we should do is keep one of them constant and vary the others. Well, this works out great for the isothermal case and the isopycnic case, where we keep temperature and density respectively constant. But if you look at the isobaric state and we look at this equation, we take dp dx1 and p is constant, that's going to be 0. So then we can't actually have a gravitational effect. So we have to throw that out. And instead we replace that with the isentropic state, where we look at a constant entropy, which, though it's not really equivalent to constant pressure, it still gives us something to keep constant, yet keep everything, relate all of our variables to each other in a way that we can investigate. So based on that, we come up with our equations for our isothermal, our isentropic, and our isopycnic case. And essentially the important thing to note here is that for each of these, they have a dependence on Mach number and Atwood number. And so as we increase our Mach number, we're going to increase the effects of these various stratifications. And really, as we increase the Atwood number, that'll change the stratification as well. But in this case, we're going to keep our Atwood number constant, so we'll really be looking at Mach number effects. And essentially, this works out to be, in our isothermal case, we've got an exponential background. In our isentropic case, we've got a power law background. And in our isopycnic case, we've got a linear background. And when we look at these plotted all against each other, you can see that in the low Mach number states, so naming the Mach of 0.3 and Mach of 0.6, there's not that much of a differentiation in the stratification. It's really when you increase this Mach number significantly to 1.2 especially, where you can see hugely widely varying states from these effects. And then if we look at the density fields as well, we can also see essentially the same thing, except in this case, our isopycnic case remains constant because constant density. So what we can do is, what we'll do is we'll break this down by our three different stratifications. We'll start with our isothermal results. And for this, we'll start off with a Mach of 0.3. And we'll look at the effects of Reynolds number. And so we've got our low Reynolds number on the right, on my right, on your left, and the high Reynolds number on your right. And so you can see that as they begin growing, really the Reynolds number, in essence, just controls how small of a scale we get. in this case, you can't really see much of a difference in the growth rate of the tip of either the heavy fluid going down, which I'll refer to as the spike, or as the light fluid going up, which I'll refer to as the bubble. Across the Reynolds numbers, that remains relatively constant, but it does change the formation of the scales at the smallest level, and we get much more detail from our high Reynolds number case. But when we come and we investigate instead the effect of the Mach number on this case, you can quickly see that this has a much more wide-reaching effect, in which as we increase the Mach number, you can immediately tell that the growth of the instability is very stunted. In the high Mach number case, it's able to only grow a very, very small amount, whereas in our low Mach number case, it's able to continuously grow and not really see much of an effect of this background stratification. Now, if we actually plot the position of the tip of the bubble and spike over time, we can compare all four of these cases and see that essentially, besides our low Mach number case, they all asymptotically approach some sort of limit and become completely suppressed at some point. But you can even see that for our low Mach number case, that compared to the incompressible case that I mentioned before that Daniel and his collaborators worked on, that it's even suppressed based in compared to that. That our lowest Mach number case, though it's near the incompressible limit, it's not completely incompressible. And then we can also compare the effects of this in dimensionality, in 2 dimensions versus 3 dimensions. So here I show our Mach of 1.2 in 2 dimensions and 3 dimensions. And you can say, you can see that qualitatively that they follow the same trend, that they still end up at an asymptotic limit and they can't grow much further. Now, the 3D case is able to grow slightly further in its distance, but that's just because when you add the 3rd dimension, you just have much more potential energy to drive, to convert into kinetic to drive these cases further. So based on that, we can move on to the isentropic results.
Really quick.
Yeah.
Is the Mach number your measure of how compressible your fluid is, or is it a little more subtle than that? Yes. So it measures how compressible the fluid is, but then it also measures how. But that relates directly to how much it's stratified. So you kind of can't separate the two. So as you increase the compressibility of the fluid, more or less, you end up with a greater stratification, and so they go hand in hand. Yeah, Adam.
Was this plot for the spike or the bubble or?
This is for just the spike, just for clarity. Yep. And so you'll see a similar trend on the bubble side as well.
So I have a question.
Yeah.
What is the Reynolds number?
The Reynolds number is 20,000. No, that's a lie. That's my bad. It's actually 5,000 for this case. I misspoke. This is a comparison of 5,000 to 5,000.
Okay, so Scott.
Yeah.
About the Mach number. So how do you control the Mach number?
How do we control the Mach number? So in our simulations, what we actually do is as opposed to before I showed in the definitions, I showed the non-dimensional forms of the pressure and density. But what we actually do is in our simulations, we run with a dimensional version of our pressure. And we change the Mach number by changing the interface pressure. And then for our post-processing, we then reconvert that back into the non-dimensional form.
Okay, so then it is the response, the level of the compressibility of the fluid responds to the change in the pressure.
Yes, it responds to the change in the interface pressure. Yeah. Yep. And then any more questions? Cool. Then moving on, we can check out the isentropic results. And you'll see in this that the low Mach number case hasn't quite proceeded as far as the higher Mach number cases. That's essentially because the low Mach number case is 10 times more expensive to run than the high Mach number case. Essentially, you'll see in these results the difference in the number of iterations my solver needs to take to get to the endpoint for the Mach of 0.9 is about 200,000, whereas for a Mach 0.3, it's more along the orders of 2 million. So we start off with our initial isentropic state, and as Daniel just brought up, we still, since this is no longer isothermal, but we still use the isothermal Mach number definition, we change this we change the Mach number by really affecting that interface pressure, and then that still affects the actual stratification. But you can see after watching that simulation that this has a very, very different response to the increasing Mach number. We actually get an increased growth in our spike given the increasing Mach number. And then our bubble stays about constant regardless of our Mach number. And we can really see that when we investigate further and look at the same bubble and spike plots over time. Our dashed lines here that represent the bubbles, they all remain very close to each other. The lower Mach number cases grow slightly faster for the bubble side, but in terms of the spike, we have the exact opposite effect, where with our high Mach numbers, they start off initially slightly suppressed, but as time goes on, they accelerate faster and faster. And then we can also go through and then investigate our isopicnic results. Same thing as before, our Mach of 0.3 simulation isn't quite to the same point, but we go through and we run our simulation, and we can see that immediately we have an even more different effect in these simulations, in which both our bubble and spike accelerate over time in comparison to our Mach number. So as we increase our Mach number, both the bubble and spike side of things are able to grow at a faster and faster rate. And this we can really see by looking at that same plot of our bubble and spike tips. In this case, you can see that at about till time 14 or 15, we remain highly symmetric in the growth of the bubble compared to the growth of the spike. But then at that point, we then have the spike starting to really start accelerating at a much more rapid rate than our bubble tips. But then to really put this all in perspective, we can plot the Mach of 0.9 case, but with our 3 different stratifications. And you can see that the isothermal case has very much stunted growth in comparison to our isopicnic and isentropic cases. And it really puts it in perspective how much faster the isopicnic case is able to grow than the other 2 cases. It grows at a very, very highly increased rate. But the question is, we don't quite understand why. We need to figure out what's happening behind to cause these changes. And to really investigate this, what we're going to do is we're going to investigate the vorticity of the field. Now, the key about the RTI is it actually grows by the generation and propagation of vorticity. So you'll see that I left off the initial conditions because their vorticity is pretty much 0. But you can see that what happens is as the perturbation grows, it develops these vortex pairs that work to rotate the fluid to then propagate fluid downwards for the spike and fluid upwards for the bubble. And as our field grows on, our vorticity field gets more and more complicated, and we generate more and more vortex pairs to help propagate these fluids. So we can then go through and investigate what, so if we look at this slide again, what we'll do is we'll look at just the left half of one of these fields, where everything should be mostly positive, where we should have just the generation of positive vorticity. And it's important to note that in this case, our x1 direction is up, our x2 direction is right. So our positive vorticity is a clockwise rotation as opposed to counterclockwise, as is normal. So what we can do is we can average the vorticity in that half of the domain over time and look at that for the isothermal case. And so for here, just because for the isentropic and isopicnic cases, I presented a Reynolds number 5,000, I'll do the same with the isothermal case and just present Reynolds number 5,000. And so we can see that as our low Mach number grows, we actually reach a kind of asymptotic limit where we have a relatively constant average vorticity. But in our Mach of 0.6 and Mach of 0.9, they reach a peak and then begin decaying as we have a removal of vorticity from some unknown effect. But if we look at our isentropic case, we can see that we have in our low Mach number, we reach what is appearing to be a relatively constant state. We'll see what happens to that after the simulations run longer. For our moderate Mach number, we definitely seem to reach this constant state, but for our low Mach number, we seem to have a steadily increasing average vorticity. When we look at the isopicnic case, we have a very, essentially just a constant increase in our vortical fields over time. We can do nothing but generate vorticity, and we never reach this limit where we have a constant vorticity field. So to understand where this vorticity is coming and going from, what we have to do is look at our vorticity equation. So here I've presented the standard form of our 2D vorticity equation, and we're going to do some modifications to it. So first we can look at, we can replace our rho, our density, with our specific volume. And that's essentially just so we can get rid of this factor of rho squared. And it has the effect of also changing the sign of the baroclinic term. But then we can go through and split our specific volume and our pressure into essentially the initial hydrostatic state and then the fluctuation state that develops as the instability continues to grow. We substitute those into our equation, do some rearranging, and you can see that we end up with a relatively decently long equation that has a lot of terms that we're not quite sure what the effects of are. I went to in-depth in this on my actual written dissertation, but today I only really have time to get into the main meat of it. Namely, this third term here, the interaction of the hydrostatic background pressure and the fluctuating velocity. This fluctuating specific volume. This term is what really drives the overall growth of the instability and determines most of these effects. These other terms do factor in for secondary effects, but we won't get into those today. If you have questions about them, I'm sure they'll come up later. So if we look at our isothermal vorticity generation from just that term, we can see that as time goes on, we actually end up developing a lot of negative vorticity surrounded by positive vorticity. So this generation of negative vorticity actually equals out to the generation of positive vorticity. And so we end up in that steady state where we initially have constantly increasing, where we have mostly positive, and then we end up to that final point where we have a balance of generation and removal. But then when we come to our Mach of 1.2, we can quickly see that the generation of negative vorticity happens much, much faster in comparison to the low stratification. And it happens in a much more broadly reaching sense. And we end up in this state where we're actually generating more negative vorticity where we should be generating positive vorticity. And this is sapping away our vortical field and preventing the growth. But if we come through and look at the comparison of this same term between our isothermal, isentropic, and isopycnic states, you can garner even more information. And so I have them right here. I have all Mach 0.9, but I think it becomes even clearer if I replace the isothermal 0.9 with the isothermal 0.3 case, just so we can have relatively consistent looking fields. And so we can see that in the isopycnic case, we have a very, very large generation of positive vorticity, whereas we have very small amounts of the generation of negative vorticity. So that's where that complete and total growth comes from. In our isentropic case, you can see that we have a similar effect. It's more in balance, and we can see that from the fact that average vorticity grows slower. And then the isothermal cases, as I just showed. But we could take this even one step further. That explains the growth, but as physicists and scientists, we're always constantly looking for a simplified way to understand what's going on. And so I present this comic where the joke that I always hear is that physicists like to approximate everything as a sphere in the absence of friction. And so we have our field of physics calcs where they're all represented by spheres. And so in this case, what we can do is when we develop our, when we start the perturbation of our vorticity, and when we really start the growth of our vorticity, you can see that the main mechanism is that we generate this vortex pair right at the interface that really drives the growth. And so what we can do is we can try and approximate these vortices by generating our own just plain vortex pair. So what we're going to do here is we actually find the total vorticity in half the field and then match that with a single vortex and then reflect that on the other side. And then we institute that velocity field on top of the background stratification with the density jump removed. So as if we had one constant fluid throughout. And so we can simulate this for our Mach of 0.3 case for all three of our background stratifications. And you can see here that what happens is we start getting, and in this case, we're simulating spike side of things. We can do the opposite and invert the vorticity and simulate the bubble side of things as well. But what you can see here is that in our isentropic and isopycnic case, we're able to really see the growth and the transport of this vorticity going through the field as we would expect in a constant density background state. But in our isothermal case, they're not able to travel nearly as far. So this tells us immediately that the isothermal case is kind of unique in its vorticity transport. And in comparison to what we saw for our RTI results, this shows good agreement. We saw that the isothermal case is suppressed, whereas the other two cases were not. So we could take this one step further and simulate the vortex pairs for the isothermal case for a variety of different stratifications. So in this case, these dots each represent Mach 1.2, Mach 0.9, and Mach 0.6, because those are the three cases that we saw complete suppression from. And we can compare the distance that the RTI is able to travel in that stratification compared to the distance that's able to travel with the vortex pair. And we're able to actually get this really nice linear trend, which tells us, well, hey, maybe we can make some predictions about this vast area that we have nothing in. Well, unfortunately, it does work for the Mach of 0.6 to 1.2 case, and we're pretty confident that we'd be able to predict the stopping point in between any of those. But as soon as we get below 0.6, and I have other results that I don't have time to show to get into this, but below 0.6, our RTI will actually surpass this predicted growth point. And so here we've got the Mach of 0.3 spike that is just going twice the distance than what we predict. And so that kind of wraps up the isothermal, the single mode results. But then the question, one of the ones I raised earlier, was what about the modality of the problem? What if, as opposed to imposing a single mode for the beginning of the growth of the instability, what if we applied multiple modes? And so what we'll do is we'll work with the same stratifications, but we're going to apply multiple modes for the initial perturbation. And so this graph shows essentially the results from using Duff and Harlow's classical method to predict the growth factor for those equations that I showed way back at the beginning, where we had the A to I. So essentially, these are the predictions for N for our based on our viscosity and our diffusion. So we're actually using what would be the A to I for the incompressible case, so that we could have a one-to-one comparison to see how that would compare to an incompressible case. And what we'll do is we'll plot these over time, and then we'll choose the peak for a relatively moderate time, because we're really looking at, we really want to see what happens to these in the early time. And the assumption is if they can grow through the very early stages, then they'll continue to grow over time. And so we choose the peak there, and then we take a hat function and we apply that with a width of about plus or minus 10 pi almost, and we force all of our wave numbers to be a factor of 2 pi so that we're completely periodic, so we can keep those periodic boundary conditions. And then what we do is we apply this as a summation, a linear summation of our these random amplitudes that we generate for each of our wave numbers, and then we'll also generate a random phase between 0 and 2 pi to account for shift in this perturbation. And then we have this factor gamma here in the front, and that's to account for essentially applying the same amount of kinetic energy through this velocity perturbation as we do in our single mode, so that we're adding in the same amount of energy. And so we can look at what happens when we apply these in our isothermal case for a Mach of 0.3 and Mach of 0.9. And you can see that very, very quickly, the Mach of 0.9 goes through a very stunted growth, which is what we would expect, whereas our Mach of 0.3 starts growing wider and wider. Again, we need to investigate this further. So we look at essentially the maximum height of the bubble and spikes. We look at all the bubbles and spikes, and we take the max of each. We can plot those over time, and we can see that our Mach of 0.9 case is asymptoting, as we expect, and our Mach of 0.3 case is having some relatively continuous growth. We can then compare this to the stopping point that we saw in our single mode for the Mach of 0.9, and see that our multi-mode case grows even less than what the single mode case would, which makes sense because our single mode case is essentially the maximum growth that we could see from a perturbation. And then our Mach of 0.3 has already made it past this spot. And so we can then begin taking kind of a statistical approach in which we can average the fields and view them as one point. And so here we've got the species mass fraction plotted for the Mach 0.3 and Mach 0.9. And we can notice that up about to
T is equal to 6 between the two, we have very actual similar results, where we have a very similar spread of the two species. But then past that, as we would expect, the Mach of 0.3 starts growing further. The two fluids start getting farther from each other. But I think this really becomes much clearer when, as opposed to the mass fraction, we start looking at the density. And so here, you can see that in both cases, the small jump that existed in our density starts getting washed out. But what we can do is zoom in even further and see that in our Mach of 0.9 case, the density jump is completely washed out by the time we make it to a time of 10 seconds. And that we're left with a completely stable background stratification. The entire instability mechanism is erased, essentially. In our Mach of 0.3, you can see that we're trending to that same point. We just have a lot further to go before we can get to that actual stable stratification. But you can see pretty readily apparent that our large jump here has become maybe a couple of very small jumps. And so we're just losing out on a lot of the instability generating mechanism. But just as before, to really understand this, we can see it much clearer if we look at the vorticity. So here we have the vortical fields plotted, and we can see essentially that the Mach of 0.3 is just able to generate a lot more vorticity than the Mach of 0.9. But we can really see it clearer when we take an average. So in this case, as opposed to averaging over half the field, what we'll do is we'll average over the magnitude of the vorticity. So we're averaging both the positive and negatives as one, with both of them being positive. And so we can see that in the Mach of 0.9, even with this, we're seeing the general trend of the removal of vorticity over time. Whereas in the Mach of 0.3 case, we're seeing the same removal, but it's happening at a much, much slower rate. And this comes about from the same exact mechanism as we saw before. That same term of the equation still is the driving growth behind instability. So you can see that in these cases, actually, the generation of vorticity happens pretty much exclusively in the very, very early times. We peak very quickly at 2 seconds, and then we just begin decaying to a very small amount of vorticity generated. And so these results are in good agreement with a paper that was just recently published by Gauthier, in which he saw that a multimode perturbation in a background stratification, what it would end up doing in an isothermal, in a strong isothermal background stratification, is it would begin growing, and then it would be suppressed, and then end in kind of a decaying, mixing, turbulent regime in which essentially you just had the two fluids mixing, but the velocity being removed over time. And we're seeing that same sort of effect even in the Mach of 0.3 case. You can see that we're tending towards a very low amount of vorticity production. And I anticipate that as this simulation carries on, we'll actually have an even further and further decrease as it gets wider. So what does this all mean? How can we wrap it all up? Well, so in conclusion, today I presented results based on high fidelity wavelet-based DNS productions that were performed for compressible and miscible RTI. They were carried out for all sorts of stratification types and all sorts of strengths. The key for the isothermal stratification is this led quickly to a complete suppression of the instability. Whereas for isotropic and isopycnic cases, we actually saw an increase in the growth of our instability with the Mach number, with the isopycnic case being particularly strong in its increase in growth. We then went on to just investigate the multimode scenario in the isothermal case, and we saw that essentially it leads to a mixing in a regime that becomes bounded and is relatively, it doesn't grow very far. But really the key is that we can describe all of these effects through the vorticity transport, but specifically that fluctuating specific volume term. So how can we go back through and think about applying this to our engineering scenarios? Well, if we think about our U-shaped jet burners, well, we wanted to maximize the mixing. We want to maximize the instability growth. So for that, we'd probably want to try and instate an isopycnic or isentropic background state. Whether or not that's possible, I'm not an expert on U-shaped jet burners, so I'm not sure. For our ICF, we wanted to minimize the growth, so this hints that we want to try and use an isothermal state. Well, unfortunately, an isothermal ICF reactor would be impossible. Can't do it. So how we actually need to go about suppressing that instability growth still needs to be investigated. Practically, isothermal stratification never going to happen. And then for the supernova, I guess we're closer to understanding what's going on there. Nobody really knows what goes on in supernovas, but we're one step closer to being able to predict how those are growing and developing. So in terms of the future work that needs to be done, so the first paper about the isothermal stratifications, that's pretty much ready to be submitted. It's been kind of put on the back burner as I was finishing up writing my thesis so I could actually defend, but that would be probably submitted within a week or two. In terms of the stratification types, comparing the isothermal, isopycnic, and isentropic, that was actually already published in an AIAA paper with the results that I presented in my comprehensive exam, in which I used a much lower resolution in order to investigate them. But now that is almost in a full journal publication form in which I've used these known improved results. The only thing we're waiting on is for those low Mach number simulations to get further. And that's really just a waiting game. The analysis is all ready to be done. We just need some more time steps. And then for the multi-mode stratification, so we were hoping that just investigating the isothermal case was going to be enough. But as I mentioned before, a competitor recently published a paper where they investigated up to Reynolds number 60,000 for strong isothermal stratifications with the multi-mode. And so we realized that we're going to have to kind of expand on that paper a little bit more. And so we're also expanding that to, in addition to isothermal stratifications, to look at the isentropic and isopycnic cases as well. But in terms of long-term, what remains to be found in the RTI community? Well, after this, really the one I'm probably most excited about is looking at arbitrary background stratifications. So if you go back and think about how we had those 2 equations but 3 unknowns, well, we just happened to choose 3 convenient initial starting points to work with. But really, we could work with anything. What if we just had a temperature set at the bottom of the field and a temperature set at the top of the field and worked in a thermal equilibrium from there? What if we just had a random pressure field that we had to work with? There's an infinite number of possibilities, essentially, and investigating the mixing and matching of all those situations would be really interesting. But on top of that, in the real world, RTI also experienced a lot of other various effects, like surface tension, reactions like in the jet burners. They'll go through electromagnetic effects, and including those additional physics and figuring out the effects of those on the growth would definitely be an interesting way to go. But really, in the end, my thought is to explore these things. I've kind of pushed the possum method to its limit at this point, and it's really struggling to keep up, especially with the 3D cases. And so it's gotten kind of to the point where either the code needs to be vastly modernized in terms of its parallelization, or we just need to put it in the trash and start working on a new one that can handle all of these. But
put it on the shelf.
Yeah. You're right. Put it on the shelf so we can keep it as a trophy and maybe come back to it later. But then here's all the places where this work has been presented and published and whatnot throughout time. There's definitely a bunch of things at APS, things at Los Alamos. I've presented at the Boulder Fluids seminar at RMFM, along with AIAA and all sorts of other places. And with that, thanks for listening. Do you guys have any questions?
We'll do questions from the audience.
So the 3 different profiles that you use, the background profiles, have rather different stability characteristics.
They do, yeah.
And I wondered, I haven't looked at your thesis, but
yeah,
is that one thing that you've tried to connect? You know, the isentropic case basically has, you know, a 0 buoyancy frequency. You know, it's neutrally stable.
Right, right.
Whereas the isothermal case is very stable.
Right, right.
And the results seem to correlate quite well.
Yeah, yeah.
With that.
So I haven't actually done a complete comparison to the stability of the exact those exact conditions with the RTI. But yes, they are. I haven't actually written them into a formal way, but they are in good agreement with each other. The only one I'm not sure about is the isopycnic case. Because I mean, like you said,
well, that'll have moderate stability.
Right, that'll be kind of in between. But in this case, our isopycnic case is showing that it's most unstable. Whereas the isothermal being the most stable is what we expect, but then we probably expect the isentropic to be the most unstable, more unstable than the isopycnic, would have less stability. But we see the isopycnic and isentropic are kind of flipped. And I haven't quite resolved why that is. Yeah. Yeah, Trevor.
Scott, this is great. It's all well and good.
Yeah.
But I feel like there's one thing really missing from this presentation, and that is, has this new knowledge impacted your brewing practices?
Well, so actually in development right now, I have 2 beers that I've developed that one is called Sir Rayleigh and one is called Lord-Taylor. And they're designed to be blended together and drank as what I like to call Atwood of 0.1.
And very good to match.
Yeah, my parents got a little taste of it last night.
Was this a planted question?
Actually, no. No, it was not.
So I'm kind of swimming in all the things that are varying, trying
Yeah,
to
yeah.
understand them. And you had several different things. One was the velocity field, vorticity field.
Yep.
You also mentioned baroclinicity, like baroclinic
Yeah,
production.
yeah.
It didn't really talk about that.
Right.
I'm looking for something that's invariant that I can hang my hat on for a little bit and try to understand all the details. Is that something that...
So in terms of baroclinicity, that third term in that I talked about, the interaction of the hydrostatic background pressure and the fluctuating specific volume, that is actually, if you look at the standard vorticity equation, that's actually part of the baroclinic term. So really, you can take all this back and say that, as opposed to breaking it down and saying that's the term that causes it, if you want to take one step further, it's really the baroclinic production of the instability that causes the growth. So that is really, in the end, it's that baroclinic term that causes the growth. Yep.
I think my question is more or less answered by these 2 questions in front of me. I was interested specifically in what was, I mean, you explained it through the vorticity, like you said, and then that fluctuating specific volume and background stratification interaction. I was just looking for a little more insight on what was causing that term to be suppressed in the case of the
yeah, for sure, for sure. So if you think about it, there's essentially like 2 factors in that term. You've got either your hydrostatic pressure or you've got your specific volume. Well, the hydrostatic pressure, that's constant, and it's actually a pretty small effect. It doesn't really factor in too much. Essentially, you could think about taking the gradient of the initial functions I showed at the beginning of the single mode study. You take the gradient of that pressure field, and that's the factor that goes under that. So what really happens is the change in that specific volume term, the fluctuating specific volume. What you'll get, especially in the isothermal case, as it begins developing, so for the specific volume, in order for it to drop, you should have a negative fluctuating term for the spike going down and a positive term for the bubble going up. And what you actually get in the specific volume fluctuation is, for the high stratifications, is a positive specific volume at the very tip of the spike. And that's where that suppression really, like if you traced it back that one step further, that's really where that's coming from, that positive where it should be negative. And then if you take that further and look at the isentropic and isopycnic case, you essentially see, as opposed to that, that specific volume fluctuation staying constant, you actually see it become more and more positive. And that's really where you can trace it back one step further and see that accelerated growth.
So you're doing everything at like a low Atwood number.
Yes.
Correct me if I'm wrong, but if you had like a really high Atwood number, you might have different compressibility for gases, and then you can necessarily have like a constant
without a
number.
doubt. So when you say you get into like a really high Atwood number, like say you're using like Atwood 0.7, you'll have completely different results. And so Scott Reckinger did some cursory studies into the Atwood number effect. I think that they were just in his thesis. They were never published in a paper. But essentially, he started to see, so as you increase in Atwood number, you expect that your spike should be growing at a faster rate than your bubble. You generate a natural asymmetry between the bubble and spike. Whereas in the low Atwood, you expect them to be very symmetric. And so you actually see kind of an enhancement of that, where you get an even more asymmetrical growth with that higher Atwood numbers. But if that's the only effect, that remains to be seen. We didn't, the suppressive effects were not nearly as noticeable just because you have so much more potential energy to drive it. But it would really take a full sweep in the Atwood number to determine it.
So, Scott.
Yeah.
Oh, you are looking at me.
Yes, I am. Oh, no, I look at you over there. Yeah.
Yeah. So then then can we just say that from all your results, in addition with the previous look, that the only regime that we've ever seen suppression is this low Atwood, high Mach for an isothermal background?
More or less, that is what results say right now. Where there would be we don't really know where, say, the regime change would be, where we see the suppression versus the non-suppression. And also, in my mind, I guess it's foreseeable that, say, at like an Atwood number of 0.2 or 0.3, that it might be suppressed in a very strong isothermal stratification if you gave it enough time. And I guess an investigation that I would find interesting is, what about if we did an Atwood number of like 0.5, but with a Mach number of 10? There's no reason why we can't. So it might be that the Mach number at which we see the stratification take effect would just be pushed to a higher, the suppression would begin at a higher Mach number as opposed to Mach 0.6. Well, even Mach 0.3. It might not happen until Mach 0.5 or 1 or 3 or who knows.
Okay.
Yeah.
I was really impressed with how kind of focused your mode studies were. And I'm curious now, what was like the biggest struggle of like stuff that took you months but wasn't really immediately apparent in?
So the biggest struggle is essentially when any of these simulations are started, like, so you do a convergence study and whatnot to try and to determine like what mesh you need, and you go by that, but it's not an exact science. You don't get, especially with an adaptive code like this, you don't get like one perfectly, this is always the exact thing that's needed. And so in my comps, I actually went very into depth into essentially the symmetry of the initial conditions. And it took me probably like 2 years of running lots of simulations to find out that they were just complete total garbage. So it was like 2 years worth of running simulations for months at a time to just see that essentially what would happen is the asymmetry from the initial conditions would cause another mode to appear in the single mode case. And you get something like the tip of the spike starting to invert. Or you get like the sides of the bubble would start to like deform in an odd way. And that would really, it would really be traced back to a very slight asymmetry in the initial conditions. That was probably the most frustrating part. Yeah. Because I mean, nothing's worse than waiting for 3 months to find out that the simulation you've been running and pushing along was just complete total worthless and you got to throw it out.
And these simulations were expensive too. So every 3 weeks, Scott would present at the group meeting, and his lines would be a little bit longer.
Yeah, the bubble and spike lines. Everyone in the lab was used to it. I would present the same exact slide with the bubble and spike lines like another like 1 second out. And that would be once every 3 weeks. Yeah.
Anything else? All right, so with that, let's thank Scott one more time. And then now we can have everyone but the committee.
So we'll talk, and then I'll get kicked out while the committee then discusses my fate without me being here. And I get to stand out in the hallway with you guys and pace. Cool. And like twiddle my thumbs and whatnot. And then they'll open the door when they come to a decision or call me back in. Cool. Yeah. Yep. That's great. Yeah. All right. Thanks.
Maybe I should before it's too late.
You get to try it. You know we're throwing you a birthday party on Friday.
It's your birthday.
No, it's your birthday.
You know there's boxing in your house. It's exciting.
So now
It's exciting.
I'm gonna grab this now.
Perfect. Yeah. Thank you very much for letting me borrow it, Scott.